So let's resume our discussion. We were talking about the sum of the vectors and the same vectors joined at the tails, so we get their difference. For some of the vectors, we always join the head of the first to the tail of the second vector. So x plus y, which is the resultant of a vector, is this vector. In this situation, vectors are not parallel to each other, they're not perpendicular. So in this case, we find the resultant by applying the cosine rule. But what if we want to find the difference of these two same vectors? If these two vectors are joined at their tails and we draw a line which joins the head of one vector to the head of the other, and its direction is from y to x, then you see this is the direction and this vector is termed as x minus y, where heads are joined. Similarly, if I change its direction, keeping x and y more or less the same vectors, y minus x will be directed downwards because y appears first here. So it should be directed towards y. It starts from the vector which starts later in this expression y minus x. Y minus x may x appears later. So our vector starts from the head of this. Similarly, our vector starts from the head of y because y appears later in this expression. So it's a rule. But what if instead of the tails, vectors are joined at the heads? Like we may have a situation in which this is a vector x, but the vector y is drawn here. This is the vector y. Again, when I join the tails of these two vectors, this will be the difference of these two. This will represent either x minus y or y minus x. But if it is x minus y, its direction is this. And if it is y minus x, it should be directed downwards. Let me draw that vector as well. This is x and this is y. And this vector, which is directed downward, is y minus x. So we have talked about difference of two vectors, and there are two different situations in which we can find the difference. Number one situation is let me erase this part so you don't get confused now. From this onwards, we are talking about difference of two vectors. Difference of vectors, which means x minus y or y minus x. So in one situation, vectors are joined at their tails. This is situation one, when vectors are joined at their tails. In this case, the line joining their heads represents x minus y or y minus x. But how do you decide whether it is x minus y and it is directed upwards or y minus x and directed downwards? It depends what is required in the question. If they ask you to starting from the head of this vector to the head of this vector. So x minus y starts from the head of x y minus x, sorry, y minus x starts from the head of x to the head of y. Now, second situation is where instead of their tails, they are joined at their heads. You see, this is vector y directed in this direction, and this is the vector x directed in this direction, and they both are joined here. So this is the second case when heads are joined. Heads are joined. So when heads are joined, again, the line joining the tails of the two vectors represents the difference of two vectors. But this time it is easier if this is vector x and this is y, this is x minus y. So it starts from the very first vector, the tail of the very first vector, and moves to the second vector. By first, I mean the first that appears in this expression, x minus y. So in x minus y vector, it starts from the tail of x and moves to the tail of y. So x minus y is this vector. Applying the same rule, y minus x should start from the tail of y and it moves to the tail of x. So y minus x is a vector directed downwards. So you have questions in the exam in which vectors are already arranged either with their heads joined or with their tails joined, and you have to quickly decide what is the line that correctly describes the difference of two vectors and what is its correct direction. There are questions in the multiple choice, paper 1, in which you have to, let me quickly redo it so you remember it. For one last time, I gave you one example each, and then we move on. Suppose you have one vector A, this is vector A, and this is another vector B. The two vectors are joined at their tails and their heads are free. These are the heads of the two vectors. Let me show the arrowheads here so it is easier for you to recognize where the heads are. The two vectors have their tails joined here and their heads are free. Now, when the vectors are joined at their tails, this line which join the heads of these two vectors gives the vectors A minus B or B minus A. It is A minus B if it is directed towards B, A minus B. But if these same two vectors are joined so that the direction of this vector is towards A, it is B minus A. So same two vectors with A minus B in this direction, the difference vector, and B minus A directed from B to A. It starts, if it is A minus B, if it is A minus B, it should start from the head of B. Yeah, I should have made this direction. The rule I have discussed earlier stated that if B is the later vector in this expression, it should start from the head of B. So in A minus B, it should start from B and move towards A. And if it is B minus A, it should start from the head of A and move towards the head of B. In this situation where heads are joined, like let's say this is vector A and this is another vector B. So both vectors are joined at their heads and their tails are free. Now this line which joins the tails of the two, this is easier to remember because if it is A minus B, it simply starts from the tail of A. So A minus B is directed from the tail of A and goes towards tail of B. But if the same two vectors are joined, but the direction is made opposite, this vector is not A minus B, this is B minus A vector. So this is all about difference of two vectors. And as I said, there are numerous questions in the past papers. It will be easy for you to make sense of those questions now. Let's move on to one more important aspect of vectors, and that is their rectangular components, because in vector addition and in solving the situations in vectors are to be added, components are of great help in simplifying the situations. By components, we mean those two vectors which have the same effect as the combined as the effect of that single vector. If I have a vector, let's say this is a vector F, a certain force. We can imagine that part of the effect of this force is along this direction that we usually label as X direction, and part of its effect is along this Y direction. That means if I make a rectangle, this vector appears at the diagonal, and these two sides, which are just the two sides of the rectangle, are known as the rectangular components of this vector F. This component is usually labeled as X component, and so this is often represented by Fx. And this component, which can be imagined here as well, this is labeled as Fy because this is Y component. If we know that this angle, this vector F makes a certain angle theta with this direction, which we term as horizontal or positive X direction, then it can be seen from the trigonometry that Fx over F, I mean this divided by this, can be described in terms of a trigonometric ratio which we call cos theta, and therefore Fx is F cos theta. Those who have studied trigonometry in the AS, this is very, very simple to understand. Similarly, Fy over F, because this is perpendicular over hypotenuse, so this must be sine theta. Therefore, Fy is equal to F sine theta. That means any vector can be expressed in terms of its components. Any vector, because a vector always will always have its effect along one direction and its effect on another direction, which is exactly perpendicular to this one. So the two components are rectangular components, and they are at right angle to each other. The components are right angle to each other, when this F makes a certain angle theta to this horizontal direction, we can describe Fx and Fy in terms of F and this angle theta. Let's solve it for a few values. Suppose there is a certain force applied. A certain force is applied to, this is a block, and you want to drag it on the floor by applying a force of, let's say, 40 Newton. And for this purpose, the string that you are pulling to this side makes an angle of 30 degree to this direction, which is the floor here. So this is floor on which you want to drag this block of certain mass. What effect of this force has along this direction? In other words, what part of this force is responsible for moving this mass on the floor? That is 40 cos of 30 degree. It is this part of the force. This 40 multiplied by cos of 30 simply gives us the force which is a part of this force, a component of this force in this direction, and this part of the force is only responsible for the motion of this block on the floor if motion takes place at all. Maybe this force is too small for this purpose, you have to increase the force, but whatever component you have here will be responsible for its acceleration here. The part which is along the vertical is not helpful in moving it to this side. The motion of this block is taking place because you have a sizable effect of this force along this direction. So this is the idea of components. Sometimes you have to increase or decrease this angle in order to enhance the effect along this direction. And this is very clear from this figure. If, let's say, there is no option of increasing this force, you can increase the effect here by decreasing this angle, maybe by lowering this string to 20 degree or 15 degree to this floor. The overall product becomes larger. So if the motion is not taking place with this value of this component, maybe by decreasing the angle, you have larger value of cos, let's say cos 15, and this force, even if it remains the same, the product will be larger. So you will have larger effect. That means components will be increased or decreased depending upon what angle you choose here. Suppose you want to lift an object upwards. The purpose is to lift an object upwards. If this is the force and this is the block on which you are applying, the same block, now you want to lift this mass up. Obviously, you would like to move this string to this direction so that this component is become smaller and smaller, and ultimately it disappears, and all this force, which should be exactly along this direction, and only then you will be able to lift it up. Because as long as you have this string at a certain angle, there will be a component of this direction, and it is likely that this block is dragged to this direction. But if the purpose is not to drag it to this direction at all, you move this string entirely here, you make this angle exactly 90 degree, So this is all you have, and there is no component on this direction. That is simple. If all the force is applied along the vertical, there is no horizontal component. And if you bring this force entirely along the horizontal, there will be no vertical component. If you bring this 40 Newton here, all this 40 Newton will be used in dragging the block on the floor. So components will have different role in different situations. Let's consider a simple situation in which components will be of help in order to determine an unknown force. Suppose this is an object and it has a certain weight. Suppose its weight is 20 Newton, and you have a certain force. You have used a string here, and with this string you have tied this object here. So as a result, you have a tension in this string. Suppose this tension is not known, and I call it tension T1 in it. This is yet another string that you have tied here with the ceiling probably, and it makes a certain angle with the vertical, and that is also known. Let's say this angle is known and this is 30 degrees. This tension is still an unknown quantity, and let's label it as T2. So this is a situation in which you have two unknowns and two unknowns. This is known, this angle is known. So two knowns and two quantities are unknowns, tension in this string and tension in this string. The idea is to solve this for T1 and T2, so we know what tension we have in this string and what tension we have in this string. And components will play an important role here, and that role is that we quickly realize that this tension T2 will have two components, one exactly along this in the upward direction and the other exactly in this direction, because they must be perpendicular to each other. Now if I bring you back to this figure, you see if we have an angle here, like I had the angle theta here, this side which is adjacent to the angle is the x component or horizontal component of it. So it is used this expression in order to find its value. So this should be, this component should be T2 cos of 30 degrees. And this component, which is actually this component here, this is the sine one. So this must be T2 sine 30 degrees. So you have two equations that you form here. We can equate these two because the object is in equilibrium, it is at rest. So the sideway, the rightward forces should be balanced to the leftward forces, upward forces can be balanced to downward forces. So one equation that we can get from here is T2 cos of 30 degrees is equal to 20. That means T2 could be readily found, and that is 20 divided by cos of 30. And this can be worked out using a calculator quickly. This will be probably 0.8 something. So let me assume that this is close to 22 Newton. Maybe 23 if you check from the calculator. So The idea is that I have the value of T2 now. And now if I use the value of T2 here, there is another equation that I can use to find the value of T1, and that I can obtain by comparing the two forces on the horizontal. One is to the right and the other to the left, and that is T1, this is equal to T2 sine of 30 degree. So when I use this value of T2, which I assume 22 and sine 30, I readily see that this is approximately 11 Newton. So I have quickly found the values of two unknown forces simply by breaking this force into its components. So breaking a force or splitting a force into its components, or any vector, it could be a displacement vector, could be a velocity vector, or any other vector. When we split that vector into its component, it becomes simpler to handle it, and it is easier to see what is the relationship between one component with the other, and then the situation is simplified. Let's discuss one more example. Suppose you have a string which is initially horizontal, and when you hang a certain weight at the center, it develops a sag in it and looks like this. And this is the mass that you have supported from this string, because it has the same length of the two sides, so it is same tension in the two parts. And suppose the angle that we have on the two ends is also known. This is same 15 degree here and same 15 degree here. So the question is to find the tension in each part of this string. So we have divided this string into two segments. One segment is to the right of this point, and the other segment is to the left of this point. So one more thing that we need to do is we resolve each T into its components, because the angles are given. I know this component will be T, because this is 15 here, so this should also be 15 here. So these are alternative angles. So T cos of 15 degree here, and similarly T cos of 15 degrees. So two exactly cancel each other. If I, let me redraw it quickly so you clearly see it. This is a piece of string which was originally horizontal, and we have suspended a certain mass here. This segment of the string has a certain tension in it, and this segment also has a certain tension in it. We assume the two values of tension same because it is the same angle on the two sides, it's the same length on the two sides. If I resolve this T into its components, the component on this side is T cos of 15 degree, because 15 is this angle, as it is same here. So from the geometry of the figure, you can guess easily that this is also an angle equal to 15 degree, and therefore this is also T cos of 15 degrees. So T cos of 15 on this side and T cos 15 on this side, so they cancel. But one component of this is upward, and that is t sine 15. But the same component of this is also in the upward direction. So it is also added. So it is 2 times t sine 15, which we can equate to whatever weight you have supported here, and this is mg. So if I know what mass I have suspended here, let's say it is the same 20 Newton that you are supporting this time. It is 20 Newton divided by 2 times sine 15. This will be the value of tension in each part of this string. So you have questions like this in which you resolve into components, and then you find any unknown forces. But what if you have components given and you want to find the resultant from them? Let me go back to the beginning and remind you what we did when two vectors were exactly perpendicular to each other. If two components are given, like fy is one component and fx is one component, how do we find the resultant? One method of vector addition that we discussed in the beginning is that we apply Pythagorean, and the reason for applying Pythagorean is that we have a right angle triangle, we have fx here, and fy, which is just another vector perpendicular to fx, imagined here, gives us a right angle triangle with an angle theta given here. So even if no angle theta is given, I can find out the resultant force F, because I can apply this relation here, fx square plus fy square, which means F is simply fx square plus fy square whole under root. So it is the same method of vector addition that we discussed in the beginning, when we have two vectors exactly perpendicular to each other, we can apply Pythagorean. And same rule is applied to the components, because vectors, components are just another vectors perpendicular to each other. So when we want to find the resultant, we apply Pythagorean to them. And what if we want to find angle theta? If it is not given, then with these values known, fx, fy, and f, we can apply any one of these trigonometric ratios. Sine theta is fy over f. Cos theta is fx over f. And tan theta is fy over fx, which means perpendicular over base. This over this is tan theta. So theta can be found using any one of these relationships. Theta is sine inverse fy over f, therefore, and similarly theta here is cos inverse fx over f, and theta here should be tan inverse fy over fx. So this is about the components. We'll have a few more questions. I suggest you spend this weekend on this topic that we have just concluded. As far as the discussion is concerned, that discussion is complete. But yes, we need to spend a little more time practicing these questions so we can handle those questions that appear in the exam. I'll probably do a few more questions with you in the next week when we have class on Monday. Until then, the worksheet that I have shared with you, try to complete that worksheet. My email address is mentioned on it. You can submit it on that address. So I can check quickly and return so we know what progress we have made on this topic. Thank you.